Okay, so for today's class, we'll continue talking about deep learning. So for the last lecture, we go through the training process, right? How you're gonna using gradient descent, and you have to tune those parameters like learning rate, set up the proper batch size, right? So in order to achieve a stabilized model training. And we also talk about one, problem people often encounter when training a deep neural network, that is the model overfitting. Okay, so the problem of model overfitting is, I put this very simple example here. If we have two classes, right, dot and the cross here, if you train the model using the training set, right, if you achieve like 100% accuracy, maybe the model is trying too hard, trying to get a perfect accuracy on the training set. But when you test the model on the test set, right, which is unknown data points, and the decision boundary is going to be, very complex, but is not able to generalize well or, separate these different classes well on the test set, right? So that's, overfitting is related to the generalization capability of your model, okay? So in general, we want to have a very good accuracy on the training set, but we don't want the model overfitting your training data. We still want the model to have very generalization capability on the test set. So that's the most important thing about model training, because after all, we care about the test accuracy, right? We are using the model you trained to predict, the unknown, the new data points, right? But for the training, we already know the label. We don't care about that, right? We care about the test accuracy. So there's a couple of strategies we can use or typically used to prevent model overfitting. Okay, so one is the weight decay, right? So usually overfitting is because the model may have some, the parameter has some large weights, right? A couple of weights dominate the model, okay? So we can using this kind of weight decay, right? Because you can add this term trying to penalize the parameters, has large weights, right? Because we incorporate the magnitude of these model parameters in the cost function, right? So if you have a large weights, then you encounter a large cost, right? So this parameter will be penalized, okay? And we also have the technique called dropout and also early state stopping, which we'll discuss, next. So for the early stopping, by the name is you want to, stop the training early, right? Let's say you set the training epoch, right? Remember we talked about in the training, you can specify the training epochs, right? How much round you want to train this model. One epoch means you iterate the training set one time, okay? And typically we have training, validation, and test set, okay? So we know the training and the testing set. So, but what is the validation set here? So usually the validation set is used to do some model, tuning, okay? Because the testing set, right, usually we don't have the ground truth label, right? The test set is to evaluate, using your model to predict the labels, right? The validation set will also come with the ground truth label. So you can test your model on the validation set and see, or maybe monitoring the loss curve or the accuracy curve, okay? So let's say, I have a training set and I have a validation set. Okay, validation set is usually very small as compared to training set. And as you can see here, right, so we have this arrow, or maybe you can consider this as the loss, right? The training loss is gradually, reduced, which is good, right? We want your model, over the learning process, the loss will be reduced, which means your model are learning something very meaningful, able to make correct prediction, right? But if you see here at this point, when every epoch, I can do a evaluation on the validation set, right? I can get this error on this validation set, right? As you can see here, this validation set error is also decreased, which is good, right? Which means consist with this training set. But during the training, at this point, the validation error began to grow, right? Increase. And this is a sign that your model is overfitting, right? Because you're trying very hard to make the training error keep reducing. And in this case, the model decision boundary or hyperplane become very complex, right? It's not able to generalize well, right? So that in this validation set, starting to make a lot of errors, right? Because very complex decision boundaries and starting to make more errors. So you will see this error begin to increase. So if you see this kind of phenomenon, right? So maybe after here, the validation's error is starting to increase, then you want to stop here, okay? And maybe using the model at this particular training epoch or checkpoint, we call it, and using that, for the testing. Okay, because at this point, your validation error is still very low, right? It's not starting to, increase, which means the generalization, capabilities still are good. So you want to using that model for the testing. Okay. Yes, so the validation data will be different than the training. How do I close this? Okay. Yeah, because if you use the same data as the training, then you won't see the accuracy drop, right? Because the sample is just the same as the training. Then you have reduced the error, then you apply to the same data, you will see this, same reduced error, right? So the validation is trying to mimic like the test set, right? This is like a new data set. I want to see how my data perform on the new data set, okay? So that's the purpose. And, student may ask, why not using test set to tune, right? Oftentimes we have, if you want to compute the testing accuracy, right? You also have the ground truth label for your test set, right? Why not just, have a training epoch, different checkpoints and test on your testing set? Well, yeah, for research purpose, right, we want to compete with different method, right? We need the ground truth label for the test set, so you are able to compute the accuracy. So you are able to compare your method with other, comparison approach. But if you think about in the real world applications, right, when you predicting label for new data, you don't know that ground truth label oftentimes, right? For example, I have an action recognition or anomaly detection system, right? I want to deploy on the surveillance camera, right? The future data coming, I don't know what that anomaly is, right? What that anomaly event that is. What I can only trust is your trained, model. Hopefully, you are able to predict very accurately. So if you are using the testing set to tune your model, it is considered cheating, right? Because you are using the testing ground truth label to tune your training data set. So this is not the, the correct way to do. So typically we'll have a validation set. This could be taking maybe 5 or 10% from your training set, right? So let's say you have maybe, 1,000 of training samples, right? What you can do is maybe taking a small amount, like 5% of this 1,000 training samples and make a validation set, right? Then you're using the 95% samples in that training set to train your model, right? And to validate what's the best learning rate, when to stop your model training, right? And based on this validation accuracy or loss. Okay, once you identify the optimal training parameters, right? What's the best learning rate and the batch size or training epoch, and you can reuse or you can directly using this optimal parameter train on that 100% training data set. Right? Remember, we are using set aside 5% of data for validation, right? But eventually we don't want to waste these 5% of data, right? In the beginning, we just want to leverage this 5% to tune the parameter, okay? Once we identify the best parameter, we'll just take that to retrain your model on the 100% training data to get the model, okay? So that's typically how the process, when you do this kind of training, your model, okay? So that's the early stopping that basically you can using a validation set to monitor your training loss. Okay, there's also a common operation that is called batch normalization. Just like any machine learning technique, right? If you're doing classic machine learning, right, using supported vector machine or logistic regression. In the beginning, you want to do some data pre-processing, right? In machine learning or data science, data pre-processing is very important, right? Data whitening, right? Subtract the mean, normalize the data at a specific range, right? And in the norm distribution. So the batch norm have the similar idea, right? So in this batch, we want to, compute the mean and also have the mini batch variance. So we normalize the data. So it is proposed like trying to mitigate this kind of covariance shift issue. And it is being kind of standardized in the modern neural architecture, like the ResNet, VGG different networks, right? People using conv and the value activation, then we're also using a batch norm, right? To normalize the data for the particular layer. Okay, so this will the batch norm will be very useful to make your model learn better. Also, maybe have faster conversion speed. Okay. And for the batch norm, it's very simple, right? So you just call this batch normalization layer, and you are able to do this kind of batch norm process. Okay. And another technique is called a dropout. So by the name is we want to drop something out of the network, right? So this is used in the training stage. Okay, so here I just give you this very simple fully connected feed-forward network. Okay, and these are the neurons, right? So in the training, each time before we update parameter, we want to randomly drop some of the neurons. Okay, we have some probability, right? Maybe 50%. Each neuron has the 20% of a chance to be dropped out of the network. Okay, so here cross means at this point this neuron will be removed from the network, right? So all these connections will be, removed from the network, right? It's just like you are manually remove some of the neurons from these networks. Okay. And so once you remove these neurons or drop out these neurons, right, the network structure is changed, right? It's become thinner, right? Because we remove some of the neurons. Okay, and we're using this, structure for the training. Okay. And because we do this during the training process, every time we drop different or we randomly select the neuron to drop, right? So you'll end up with different, structures during the training. And during the testing, we don't want to remove any of the neurons, okay? Because during the training, we do the dropout. Each neuron has a very strong, learning or representation capability. We want to leverage that, capability of all the neurons. So during the testing, we don't do dropout. So dropout is only applied during the training. Once the training is done, we're just using the full network to do the testing. Okay. So you can think of this dropout is kind of like a model ensemble, right? So during the training, right? So we have maybe this batch, mini batch, we have this network one, right? Because of the random dropout of some of the neurons, okay? For another mini batch, the dropout of the neurons has changed, okay? So we result in a different network architecture, right? You can do this, you know, for many training batches, we have different, you know, networks with different structures. So it's kind of like an ensemble kind of way to kind of regularize the model training. And so here are some of the reference if you want to learn more details about dropout, and you can go through this kind of references, okay? See the questions here. So yeah, the validation will be more compact in general. Yes, so like I mentioned, right? So you can take like a 5 or 10% from the training data set aside, or maybe some of the data set, if you encounter, they already specify this is the validation set, and then you don't have to, you know, reallocate a small portion from your training data. But yeah, you cannot using the testing data to tune your model, okay? Yeah, cross-validation is also related, right? The validation set is you have a dedicated set for validation, right? But cross-validation means you have a training set, right? 10,000 images, right? And if you do 10-fold cross-validation, right? 10-fold means you divide your training set into 10 subset equally, okay? 10,000 divided by 10, like 100, right? 100 samples per fold, right? Then every time you take one fold from that as the validation and using the rest 9-fold you know, set for the training, right? You iterate 10 times, right? So each set get a chance to be a validation set. Then you check the average performance, right? What's the best you know, parameters for tuning the model, okay? Yeah, the dropout, you know, sometimes will, you know, reduce the neurons, right? But the idea is that, you know, the co-adaptation concept, right? So maybe 5 or 10, several neurons, they team up together, right? They behave, you know, they only behave very strong when they are a team, right? Let's say like 5 or 10 together. We don't want that, right? The idea is that we want each neuron maximize their, you know, capability, right? Each neuron is able to learn very informative, you know, representation, so that, you know, the model is able to make very accurate prediction. Not want like a couple of neurons team together, then you are able to learn something meaningful, right? So that's why we randomly drop some of the neurons. So there's no chance for co-adaptation, right? Because we are removing the teams, right? Team members from the team, so that force you to each member or each neuron to learn meaningful representation, right? The network, you know, representation capability can be, you know, stronger by doing this way. Yeah, dropout is not necessary, like I mentioned, right? You have different ways to do the regularization, right? Some of the network modern architectures already have batch norm, maybe some other weight decay, right? In optimization, they have some momentum they are used, then dropout may not be necessary. So yeah, dropout is just a way, right? So if you see there's overfitting, then that's a method you can use to prevent overfitting, right? Obviously, you have to, you know, test where you want to, you know, input this dropout layer, right? How much probability you want the dropout layer, okay? So those are some of the details, you know, you can read those literatures to understand more. Okay, how do I close this? Okay. So before these kind of regularization technique is kind of, you know, structure or network related. So there's another category which, you know, use trying to address from the data level, so which is data augmentation. It is also very common used in deep learning training. Because we know deep learning are very data hungry, right? It's a data-driven approach. We need to use a lot of data so that we can learn something very meaningful from the data. Okay, but for some of the applications, like especially for medical image processing, right? It's very difficult to get a large amount of data, right? For example, the patient data, is very, scarce, right? Maybe some of the rare disease, we don't have a lot of examples like just these natural images. And for small training data set, there's a high chance of overfitting, right? If you have a lot of parameters, but your training data set is very small, then there's a high chance your model is going to be overfitting. So one way from the data perspective is we can do some data augmentation, which essentially is increase the training data set size, okay? And there's a very common data augmentation technique, right? We can do the mirroring, right? Just like you are, watch yourself in the mirror, right? So we can also do random cropping, right? So basically you can, crop one region at different locations of this image, right? And to make new images, right? And we can also do some rotation, shearing, or warping, right? So you end up with, this kind of, new images, right? Although the semantic information won't change, right? We don't want to change the semantic information, right? Your cat should be still a cat, right? A dog should still be a dog, but it just maybe the orientation, the position, or the size may change a little bit, or maybe the color distribution will change a bit, okay? Yeah, so this one is color shifting, right? We have RGB 3 channels, then we can, adding some of the disturbances into different, channels so that the color will be changed. And here, this paper did some extensive evaluation, right? We have different color space, right? RGB, HSV, right? Hue, saturation, and YUV lab, we have different color spaces. Okay, we can convert the image original RGB into a different color space, right? To generate a new image, right? We can, using this kind of different color space conversion and see, which one give you the best result. And this one technique is called random erasing, right? So here, this is original input, right? A fox, a plane, right? We randomly, select a region and crop this region, right? And you can either fill that with a 0 or maybe fill this region with random noise, okay? And the shape, the size can be changed, right? Actually, some parameters you can tune, which give you the best result, right? By doing this kind of crop, erase some of the part, you are able to generate more images, right? So what's the intuition for this random erasing? So if you look at, okay, so for this erasing, right, I erase some of the portion of the face of the fox, right? Maybe part of the ear and one eye of the face. So, if I feed this data to the network, right, and, it kind of force the network to try harder, right? Pay more attention to other regions, right? If I give you the original image, right, maybe your network is trying to focus on this particular region. Maybe it learns to, okay, this may be some of the salient regions. I can purely focus on these important regions to make a prediction. But if I remove this, right, I force the network to think about other important features, right? Maybe the tail or the body shape, right? Or maybe other features, right? Like the mouse, etc. right? Trying to force the network pay attention to other regions so that can learn other meaningful representations to represent this is a Fox image. So that's the intuition behind this kind of random erasing, okay? And we also have this, this automatically learned policy, how you can generate or augment the data, right? So this one, because we have so many operations we can use, right? Translate, rotate, color jittering, right? Contrast enhancement, brightness enhancement, etc. Right? We have all the different operations we can use. And if we want to apply these techniques for a certain sequence, right? What's the best way or best sequence we can apply these different operations, right? So this paper using this kind of reinforcement learning method, trying to learn a policy, to apply these different operations in such an order, the augmented image will give you the best benefit or improve the model generalization capability. And cut mix is also kind of based on the cutout and a mix up, right? Mix up is basically you have by looking at this example, right? You have two images, mix them up together, right? You can, maybe see this, there's a cat, right? On this portion, there's a dog. Original is a dog, right? I mixed this with a cat, maybe the cat image 50%, dog image 50%, right? Of course, the label, I will also have this kind of ratio proportion to that. So this also trying to force the network learn very unique representation to tell this is the feature belong to the dog and this is the feature belong to the cat, right? Cut out the same idea, right? So we cut one region, right? Now we are not depending on the head, which has very important feature to determine a dog, right? Here we don't have that, right? What we do, we force the network to learn, look at the other regions, right? Maybe the body, the tail, the leg, etc., to learn meaningful representation to recognize this is a dog, okay? Cut mix basically just, instead of just pad 0, we added the same region, but with a patch from another, image. This is a cat, right? So then we also, make that label proportionally to this region or the size of the patch. And this shows these data augmentation method will, improve the classification accuracy. Okay, so this green one is how much it is able to, improve by doing this kind of data augmentation technique. Okay. So I list these two resources. If you're interested, you can, read more with different data augmentation technique, and they also have code available, right? You just have to call this function, to perform this particular or many types of data augmentation technique. Okay.
Dr. Chen, I have one question.
Yeah.
So, are these transformations like more related to like general deep learning or like for particularly medical imaging?
Yeah, this is general, deep learning, right? Medical image also, can benefit from data augmentation as well, right? When you have, a very small training data set, you can also using, data augmentation to help you kind of increase the training data size.
Yeah. I mean, so there will be some like special transformations for some specific medical data sets, right?
Yeah, so there are some specific, like there's some, you have to be, think wisely, right? For example, if I want to detect or classify there's a tumor, right? There's a tumor in this lung, right? And maybe this, lung tumor is not very distinguishable as compared to the normal lung, right? If you do the cut out, right? Maybe you cut like the entire portion of the lung, then you don't have any useful information for you to tell this is, like a abnormal or diseased lung images, right? Maybe you have to using other technique like rotation, right? Or maybe some small translations, or maybe some color jittering, that's maybe a better choice, right? But if you cut, then maybe the tumor region already cut out, right? The left one is just normal region. Then there could be confused the model, right? Why this is a normal one, right? So you have to think about the specific problem you have, right? And apply the proper data augmentation techniques. Does that make sense?
And it will be like more like domain specific in particular.
Yeah, so you have to think about which one is best suited for your application or for your particular problem, right? Like mirroring rotation is okay, right? We do not change any of the content, right? We just maybe change some of your, geometry of the data. Okay.
Yeah, sure.
Okay, so next, I also want to talk about transfer learning, so which is also a very common technique when dealing with a new data set or new task. It also works well, if you have a very small data set, okay? Data augmentation definitely will help, right? But how it may not able to give you significant boost, right? Because no matter how you modify the data, right, you don't have a lot significant new information injected to the data. But transfer learning give you another direction that is able to help in this scenario. Okay, so basically we want to transfer the knowledge from a related task that has already been learned, okay? So let's say we are doing medical image classification, okay? So we are classifying maybe pneumonia from, chest x-ray, okay? We don't have a lot of data, right? So what we can do is, we know there's an ImageNet data set, right, which contains like 1 million of training data, okay, from 1,000 classes. And we already have some of the model, like different CNN architectures has been trained on ImageNet data set, right? It's able to learn very good representations of the general image, right? We want to transfer that knowledge to our domain, which is medical image classification, right? We can using the pre-trained model weights as the initialization of the CNN. Instead of random initialized train from scratch, we can leverage that pre-trained model, okay, and for our new task. So there's when you do this kind of transfer learning, there's a couple of choices you can use, mostly two major ones. That is, one is you can using CNN as a fixed feature extractor. So that means let's say you have a ResNet 18 as your CNN architecture, right? You have a pre-trained model, ResNet 18 on ImageNet, and you take that learned model and apply it to your new data, okay? You run that model through your new data, but you don't run till like the end doing the classification, right? This is the FC layer for the classification. So before that, you maybe have another layer, right? This is a feature vector F here. Of course, you have other count blocks, etc., right? So you basically run your input through the network till the last, before the classification layer here, you're using this as a feature extractor, right? You run this network, pre-trained network, you own your new data, and you take this feature as your feature representation, okay? And maybe you can later connect to a linear classifier, right? You don't even have to, using the deep network, right? Maybe you can just take this feature and train a logistic regression or linear supported vector machine, right? So this way, CNN is just act like a feature extractor, just like other classic feature extractor, like, histogram of gradient or edge detector, right? Detecting those features. But now we are leveraging some pre-trained model to extract the features, okay? Another strategy is we want to do some fine tuning, okay? So here is what I mean, for these two different categories. So this is the input, let's say this is ImageNet, right? Input is ImageNet data set, and we are doing ImageNet classification, okay? So that's the task A. And for this network, we've trained on ImageNet. And now the B task is doing medical image classification, right? So we want to leverage this pre-trained model. So we take a couple of layers from this pre-trained model, right? And we kind of freeze the weights, right? We don't change the weights, right? Remember, the parameter from the function is what we want, right? So we freeze the weights, and we only, for the new task B, right? We have the new medical image data, right? We only train the rest of these new layers, okay? So these two layers are adapted from, this pre-trained model, okay? We don't change the weights. So the backpropagation ends here, right? We want to freeze these weights. So all you learn for your network is these new layers, okay? And another strategy is that we can, backpropagate, to the end, right? So we take these pre-trained weights, but we can do some fine tuning, right? We essentially, instead of freeze them, right, fix them, don't change, we want to fine tune it, right? We can also fine tune these two layers. Basically, we're just using the pre-train as initialization, and we can fine tune these weights for this, our task, which is medical image classification, okay? So, so there are some general guidelines, right? So if we have a model A trained on the data set, right, how do we apply transfer learning to data set B to create a model B? So here I have some very general recommendations, okay? So if your new data set is small and similar to the original data set, and we can train a linear classifier on the CNN codes. So which means you using the CNN, pre-train the CNN as the feature extractor, like we talked about before, right? Using that as feature extractor, extract the features, and you can train a linear classifier on top of these CNN extract features, okay? And the reason is that, okay, because the original data is very similar to our new data set, right? So a lot of information, semantic information or representation learned from the original data set can be applied to our new data set, right? So like those different edges or high-level representations can be applied to our new data set. So it's not necessary to fine-tune the model. So you can just directly take the features and learn a linear classifier for your new data set. The reason you have to learn a new linear classifier may be because the number of classes will be different, right? Maybe the original data set have 200 class or 1,000 as ImageNet, but your new data set medical image maybe only have 10 classes, right? You cannot directly take all the network. You have to train the last linear classifier layer to classify your new data set. Okay, so if the new data set is large and similar to the original data set, then you can fine tune through the full network, right? So you basically take the pre-trained model weights as initialization, and you can fine tune it through the entire network. So another cases like new data set is small but very different from original data set, which is the case like if you use ImageNet as the original data set, medical image will be very different, right? The medical image can be very different. And what we can do is we can train a linear classifier here. I'm just using supported vector machine, which is very popular. You can using a linear SVM classifier. And from the activation somewhere earlier in the network. So if you have a deep network, right, you have maybe 10 or maybe 50 layers of count layers, you can take the feature from earlier networks, right? Maybe the first, 2 or 3 layers. The reason is that although data is very different, but at the lower level, right, the early stage of network, those count layers may only learn some low-level features like edges, corners, right? This will be fundamentally similar, right? No matter you are coming from the general image or medical image domain, right? Because those are the fundamental components, right? The edges and corners. The high-level representation will be different, right? Maybe the high-level representation, this is a face. Maybe for the medical, we don't have the face-like image, right? So this high-level image may not be useful, but the low-level, the common representations will be useful for your new data set. So we can leverage that and train, linear classifier. And if the data set is large, we can fine tune it, right? Because we have a lot of data, we are able to, using these pre-trained model as initialization and gradually tune this model to represent the new features from the new data set. Because of the large data, there's less risk of overfitting, okay? So here just a table to summarize what we just described here. So if you want to learn or maybe actually take a example like how the transfer learning is being applied, you can look at these PyTorch and Keras tutorials. So they have these step-by-step process, right? How can you load a pre-trained model, usually ImageNet pre-trained model, and apply it to your own data set or own task. Okay, so I encourage you to go through this tutorial so you understand how you are able to implement that in the code. So yeah, here is I list a very good paper. They specifically kind of investigate how transfer learning should be applied for medical image, right? So as you can see here on the left, this is ImageNet, right? But this is medical. Medical image, pay attention, usually pays, local attention to the regions, right? Image here, we look at the global scale, right? But for medical, for this fundus photos, maybe we just look in a small region like this, right? For the lung, we are maybe pay attention to this local region. And visually appearance, they are very different, right? So, and in this paper, they found out, they have to come up with some, specific solutions so that the transfer learning can be effective. So one solution is that instead of transfer the weights, from the pre-trained model, they transfer the scale, the range of the weights, right? So they can using these normal distribution. Basically, you can compute the mean and the variance from the pre-trained model, and using the mean and the variance to guide as a scale to guide the weights of the new network for the transfer. And also, they're also using the pre-trained weights only from the lowest two layers, which I just described, right? These low-level earlier layer or lower layers, they detect those fundamentals, right? Edges and corners. No matter what kind of images you are, that's the fundamental building blocks, right? You can build high-level representation based on the edges and corners, right? So those you can adopt from the pre-trained model, okay? So which is exactly they are doing here. And I also found this, medical image analysis, they have a pre-trained model. So it's all pre-trained on medical image data set. I think they have like 20 different medical image data set, and they train on medical images rather than natural image like ImageNet. So, but they are only for 3D convolutional neural network, not 2D. So if later in your project or in the later, programming assignment, if you're using 3D CNN, this is something you can look into. Maybe if you want to leverage some pre-trained model, and this one is a good choice, because this pre-trained model is learned based on the medical image, not the natural image, which has less domain gap. Okay. So in the next, we'll quickly go through some of the common CNN architectures.
Dr. Chen?
Yeah.
I had a quick question about the transfer learning part.
Yeah.
Transfer learning has like 3 variety of stages, right? Like a positive transfer, the negative one, and the neutral one. If you could explain me about the negative transfer and how to cope with that.
So can you explain like what do you mean like negative transfer?
Like once we start the transfer learning, like when we try to correlate two things, the part where rather than going towards the accuracy, we deviate from that, and it makes the things go worse, right? And
Okay. Yeah.
that way,
Yeah. So like I mentioned, right? So obviously you can set up another baseline, which is trained from scratch on your target data set, right? Let's still consider natural image as, you know, your original pre-trained model and medical as your target, okay? So to verify if, you know, transfer learning, you know, is helpful, what you can do is first you train your model from scratch. From scratch means you randomly initialize your network weights and you only using the medical image to train the model. Okay, you can set this as a baseline. What's the accuracy if I'm trained in this way, right? I don't leverage any you know, existing knowledge, right? I just train my network based on the data set I have. And then you can, you know, explore if ImageNet pre-trained model is going to be helpful in my case, right? You using the pre-trained model and you using that as initialization and you fine tune it and see what's the performance look like, okay? If you see fine tuning or using the transfer learning doesn't help, there's going to be maybe a couple of reasons. One is maybe your learning rate doesn't set up properly. So usually you can using a smaller learning rate when you do the fine tuning, right? Because we have a very good start, right? The pre-train weight you can consider compared to random initialization, that's a pretty decent starting point, right? So you don't want to have a very large learning rate to jump too far. You may diverge or something, right? You can using smaller learning rate, trying to modify or tune your model to fit your targeted data. And the second is maybe, as I mentioned, right, you don't want to, you know, adopt all the layers, right? You may just want to using the first 2 or 3 lower layers, right? Those are some of the fundamental, learn those edges that can be used. But the higher level layer, you have to train from scratch, right? So these are something you can think about. And at the same time, you also want to, you know, try maybe combined with data augmentation for your medical data set, right? When you do the fine tuning, if you increase data set, that may also help the learning. So these are some of the, common practice, right? You can think about, you know, when you do this kind of transfer learning, or if you encounter some of the, problem which you don't expect. Okay.
Okay. And one more quick question, does it work with smaller data sets, or do we have to every time have a large data set to work with for the transfer learning part?
Yeah, small data set works, right? So that's why I'm kind of, saying, sometimes, with the transfer learning, is particularly good for small data set, right? We can leverage some of the existing knowledge, for your small data set, because learn from scratch can be very difficult, right? Because you have limited data. So just go the previous slide, I summarized those different cases. You can follow that practice, right? Which is the best way when you actually implement transfer learning, okay?
Okay, thank you. Okay.
Hello, Dr. Chen. So, I have a question regarding the transfer learning. So, let's take like there's a VGG network, and there are some there are these layers in the VGG network. So, depending upon how the data sets are correlated with the new task and the originally trained task, we will choose like how many layers we want to drop, or like is that how we do, depending upon the data set similarities, we select the layers?
So those are the general rule of thumb you can follow, right? If you can compare how similar is the data set visually, or just by conceptually knows, right? Medical image generally are very different than the natural image, right? So, and also how many layers to use. You want to freeze maybe the first 2 or 3, or you can go in deeper a little bit. So these are based on the experience. So there's no like a golden rule, like you can just select the 2 layers. It depends on the data set you have, the target data set you have. And you have to kind of empirically to decide based on the experiment, which one give you the best performance. So these requires, a lot of experiment and try and see what's the best strategy, for your particular data set when you do the transfer learning. Those kind of general guidelines are, some of the common rules you can follow, but how exactly you should, adapt or fine tune is you have to depending on the data set you have and based on the experiment result you got, you have to adjust. Okay.
Yeah, so it's like a hyperparameter tuning or
Yeah, so yeah, everything is, yeah, this is very complicated, right? Deep neural networks. You don't like it's not just simply a very 1 or 2 rules you can set that works every time, like a charm for all the data set. There's some inherent differences, between different data set. Then you have to kind of babysitting your training process to make sure, you are achieving, the desired accuracy you want.
Yeah, thank you.
Okay.
Yes.
Okay, so the CN here, right, I list a couple of this ImageNet challenge. And so for the AlexNet and the VGG, that's the earlier CN network. Right now, people don't use these a lot because of the performance. And later we have this Inception network. So basically this one unique thing for this Inception network is the Inception module, right? If you look at this architecture, instead of just using one convolutional size, right, kernel size 3x3, 7x7, etc., they use multiple size and trying to concatenate them together. So that's the the unique about the Inception network. Also, the ResNet, which is, I would say, this is the most widely used network right now. If you look at all these applications, the top one choice to use is the ResNet, right? It has very good performance, and the ResNet has different variants, right? Based on the different layers. You have 34 layers, you have maybe 50 layers, you have over 100 layers of ResNet. So you have different variants you can choose from, based on how many computing resource you want or how much of the accuracy level you want, okay? So the unique thing about the ResNet is this called the residual connection. So you have this skip connection, right? So basically you are able to directly injecting the original input X, right, towards the end, okay? So in this, for this kind of formulation, essentially these 2 weight layers are learning the residual between your output and your original input, okay? So this kind of help in the back propagation. So that's why the ResNet is able to stack like over 100 layers. Before, like a VGG, like 19, they are not able to go very deep. But for the ResNet, they are able to build very deep networks. As I mentioned, there's a couple of variants, right? So I took this from PyTorch. So for the ResNet, if you want to load this ResNet pre-trained model, right, pre-trained from ImageNet, you can using ResNet 18, 34, 50. So these are different layers you want to use, right? Obviously, this is like the largest model, right? You have more parameters and more compute as compared to this smaller network. So depending, if you want to purely push the accuracy, deeper network may help, but you also have the computation concerns, right? You may have to choose a smaller network, okay? And inspired by ResNet, so later they have built this DenseNet, right? As you can see, you have a lot of different kind of routing or connections, skip connections, where you can jump from this first layer, input layer directly to like the last count layer, right? This kind of encourage different information flow through different layers, right? Before you kind of just doing this kind of in series or sequentially, right? So this layer, you take the input from here, but here you can also have the option taking input directly from the first layer. So kind of encourage the information flow freely in this network architecture. So the StanceNet won the 2017 CVPR best paper because of this new network architecture is also able to reduce the ImageNet classification error further. Okay. Next, I want to talk about the MobileNet, which I think is very important. Now we know that we are able to build sophisticated network, right? Deep network. We are able to push the accuracy, but in a lot of real world applications, we don't have that bandwidth or computing resource to deploy such large model, right? For example, the mobile device, right? The cell phone. Because of the limited compute and memory, we are not able to deploy very large network on these resource constrained devices. Even if we are able to deploy these kind of large models, the inference time or inference speed can be very slow, right? Maybe if I take a picture trying to recognize this as a dog, it may take like 30 seconds, right? Obviously, this is not acceptable, right? So if you took out your iPhone, right, there is some built-in feature like face detector, right? This kind of real time, right? If you took out your phone, is able to instantly detect how many people are there and highlight their face region, right? You want to focus like autofocus, right? Focus on the face region and maybe blur the background, okay? So we require real-time performance on these mobile devices. So the MobileNet exactly with this kind of objective in mind and trying to devise some of the operation that is going to be computation and memory efficient. So let's look at how MobileNet achieved that, right? So we know this, the conventional convolutional operation, right? So let's say we have a single channel image, right? Just for simplicity. And we have this 3x3 kernel, right? So you're basically sliding this 3x3 kernel across this image, right? And in each of the window position, you do this kind of element-wise multiplication, right? Do the dot product. So one thing to note is that, during the hardware computation, right? So multiplication is very expensive, as compared to addition. So if we know this, we want to reduce the number of operation of multiplication, right? So that we can reduce the compute. So let's look at, the number of multiplications for conventional convolution. So here we have this input feature map, right? So we have this DF by DF, that's the spatial resolution, height and width, or the feature map. And we also have M channels, okay? So this is a cube. And we also apply, DK by DK. So that's the spatial resolution for your kernel, for example, 3x3, okay? And because we have M channels, right? This is your input channel. Your kernel also will have M channels because then we can do this kind of convolution entirely on this input. And we specify N such different filters. So we are able to generate N feature map, right? One filter generates one feature map. So you can calculate how many multiplications are there. So let's consider the first. If I have this, input feature map, right? I specify DK as the one standard convolution kernel. If at a single position, let's just look at the very top position, the first position here. How many multiplications are there?
Between dk by m multiplication.
right? So that's dk squared by m, right? So because this is the kernel size we have, right? So we have m channels, right? If we look at each channel, we have to do the element-wise multiplication, right? Because of the spatial resolutions dk by dk, we have dk squared multiplications for each channel, then we have m channels. So that's dk squared by times m multiplications, okay? How about if I apply this one channel over the entire input, right? I just sliding across the entire input, how many multiplications? I specify here, the output feature map is going to be dg times n. So here I'm saying one kernel over the entire input, how many multiplications?
Is it like dk square by df?
Dk squared times what?
Times df, like that.
df.
Yeah.
So
Oh, never
we
mind.
know one position is dk squared times m, right? I mentioned one kernel over the entire input, right? We have to slide into this next position, right? One position generate one like output from the output feature map, right? Look at what's the size of the output feature map. It's dj by dj, right? So which means we slide like dj square positions. So we have dj square times dk square times m multiplications for one kernel over the entire input, okay? And the next one easy, right? If we have n kernels, then we multiply that by n, right? So this is the total number of multiplications it incurs if we sliding this dk by dk standard convolutional kernels over this, df by df input. Okay, so for this MobileNet, they propose this steps-wise separable convolution. So it has two stages. So one is steps-wise convolution, and the second stage is point-wise convolution. So the goal is to reduce the computation. So that's reduce the number of multiplications. And let's see how they achieve this, okay? So again, we have the same input, right? df by m channels. Instead of using the standard convolutional kernel, what it does is they specify m different kernels, okay? But each kernel is not dk by m, it's dk by 1, okay? So it's just a single channel, dk by dk, okay? And they specify m such different kernels, okay? And they apply this m, different kernels channel-wise. So here I give you a very concrete example. Let's just make it simple. This input is going to be 12 by 12 by 3. Okay, 3 is the channel dimension. If I want to apply the steps-wise convolution, I have to specify 3 these kernels, right? The channel was going to be 1. Okay, the spatial size is 5 by 5. So if I look at the first one, this orange one, I will slice this kernel only on the first channel, okay? Because this is one dimension, right? Channel dimension is 1, right? Only slice this orange in the first channel dimension. I can generate 8 by 8 feature map, right? For the second channel of the input, I apply the second one, right? This red one. I do this, across this entire input. I generate another output feature map, red one. So yellow one the same, and I generate the third one. So if we have m input channels, then we have m these kind of single channel kernels and do this channel wise, okay? So that's the depth wise convolution, right? We're doing in the depth wise, right? Each channel we apply this convolution. And what you end up is this dj by dj m, right? So dj is just the output dimension. Depends on if you are doing the padding, how large your stride. So let's just say we have dg by dg output dimension, right? And we have M channel, right? Because we have this M kernels doing this one by one channel, we result in M channels, okay? And the second step is we do the pointwise convolution, okay? So we take the resulting feature map, DG by M, and we apply the second pointwise convolution. So the pointwise convolution is that we use this one by one, but has M channels. Okay, so this is, you can consider this is like the regular convolution, except the dimension, spatial dimension is one by one, right? We, instead of looking at maybe 3 by 3 regions, we only look at one pixel at a time. Okay, we look at one pixel at a time, but we look at them across the entire channel, right? If you place this kernel here, spatially, you look at just a single pixel location, but we look at across the channel, right? We do this multiplication, and we can, if we apply, you know, n of them, so we are able to generate DG by n feature maps, right? So one filter, we generate one feature map. If we apply n filters, we generate n feature maps. Okay, so that's the ultimate output after this pointwise convolution. Okay, so let's see how many computations are there, right, for these two separate operations. So for this depth-wise convolution, this is the how many multiplications we are getting. Okay, and for the pointwise convolution, right, PC pointwise convolution, this is how many multiplications we are getting. So because these two you know, stage we are combined, right, to generate the final output feature map, we can sum them together to generate the total number of multiplications. So that's the number of, if we do the steps of our separable convolution, that's the total number of multiplications we are getting. And if we, you know, do side-by-side comparison with the standard convolution and this depth-wise convolution, so I list, you know, the numbers here, okay, and the number of multiplications in depth-wise separable convolution is here, and the number of multiplications the standard convolution is here, and this is the ratio we are getting. Okay, and if we plug in, you know, a specific number, right? Let's say we have 1024 filters, and this is the kernel size we're using for the decay, and you can see, you know, depth-wise separable convolution is like 10%, right? 0.1, a little bit over 10%, as compared to the standard convolution if we use the same these parameters. Okay, so as you can see, there's a 10 times right efficiency, right? We only have occupy like 10% of the computations. So so that's improved efficiency a lot. Okay, so that's the summary. You know, if you want to compute how many multiplications there, you can, you know, using these equations. And if you want to compute a specific ratio, depends on the parameter you specify, and you can plug in this, right, and see how much, you know, improvement you are getting if you are using depth-wise separable convolution. Okay, so this one note I also want to mention is the one-by-one convolution. So it is also commonly used for channel reduction. Okay, so if you have a feature map has a channel dimension of n, so you want to reduce the number of channel dimensions, you can apply this one-by-one, you know, by n, you know, one-by-one convolutions, and you can specify a much smaller number. Maybe I just want to using m of them, right? M is a much smaller number as n, so you end up with a k by k by m, right? For example, if you have a 1000 input channel dimension, right? If I using m can be 10, these one-by-one convolutions, so I can reduce the channel dimension from 1000 to 10. So that's, you know, a lot of time you will see for some of the network, they mentioned this bottleneck structure, right? You have a very, you know, wide channel dimension, then you can using 1x1 convolution to reduce that channel dimension. So it's very common technique to use, okay? So here is a number, this table kind of give you a comparison, right? In terms of the ImageNet classification accuracy and the number of parameters, right? How many parameters are there and how many multiplication and additions are there in total. So for the MobileNet, as you can see that it is able to, you know, greatly reduce the number of parameters and also reduce significantly amount of compute, right, as compared to like the VGG and the GoogleNet. So that's why MobileNet is very popular if you want to design some of the lightweight architecture, which I think is very important for medical image computing, right? Medical image usually are very high resolution, right? The image like CT/MRI can be very high resolution. And also there can be a lot of slices, right? Maybe 200 slices. If you have a large network, then process one example or one sample can be time consuming, right? If you want to detect if there's a brain tumor for this MRI scan, if you have a very large network using conventional convolution, the inference time could be over a minute or even more, right? But this may not be acceptable for medical applications, right? Because you want to have some diagnosis very quickly rather than waiting a couple of minutes. So this kind of lightweight or computation efficient architecture is very desired for such applications, okay? So based on the MobileNet V1 I just introduced, they also have some improved versions. So they have MobileNet V2 make some modifications based on V1. And also recently they have MobileNet V3, which is based on neural architecture search, right? They want to search what's the best architecture for MobileNet V3. So if you're interested, you can look at these papers, what's the new component as compared to the original V1. And here I've also give you some of the common networks models in PyTorch, right? So if you want to using these different architectures, you can specify which network you want to use, right? We have ResNet, right? ResNet have different variants, and you also have MobileNet, okay? If you want to build some lightweight, efficient architectures, you can use in MobileNet, okay? If you're using Keras, the same, right? You have different ResNet, and you also have, MobileNet V2, and also DenseNet. Okay, so here I'll also give you some of the tutorials and step-by-step implementation for doing image classification. So you can follow these tutorials or examples when you do your first programming assignment, which I will release later today, okay? So the first programming assignment will be doing image classification, medical image classification. So these are some very good examples for you to follow, right? How to load the data, load the pre-trained model, if you want to using pre-trained model, right? How to specify which network you want to use, right? ResNet or MobileNet, and how to, using different loss function, cross entropy, or maybe other loss functions you want to use, and then monitoring the loss curves during the training, and also maybe using validation set to monitoring your validation error. So these are some of the very good resources I recommend you to go through. Okay.
Yeah, Dr. Chen, I have a question.
Yeah.
So like I have been seeing recently, like the many models that end with the next, like ResNext or something,
Yeah.
ConNext. What are these like extensions like X and T at the end?
Yeah, the ResNextNet is basically some improvement over ResNet. SCNet is also after things after DenseNet, squeeze and excitation network. So they are introducing some attention model, which I will discuss about in the next lecture, right? Some attention mechanisms, which are very popular. And also I will briefly talk about getting a lot of hypes in computer vision, which is the transformer, right? The vision transformer. So I will touch upon a little bit on that. So when you're reading papers, some of the review or some of the papers you present, you know what those concepts are, right? Where do they come from? Okay.
So basically, so these NEXT that ends with like, these are like improvements over those networks, and they are like very recent works or something.
Yeah, so a lot of recent improvement is just based on this ResNet structure. So you wouldn't see significant improvement, right? Mostly like how you maybe adding more attention or maybe have some other modifications on the some operations, but they don't introduce anything like a very significant. So skip connection is, when people saw ResNet, people never thought about using skip connection, right, to injecting your input directly to the output, right? So they will consider this is very novel. But later there's, I wouldn't say significant changes or modifications in terms of neural architecture. So you can look into their detailed papers and figure out like what are the specific changes they are making.
Yeah, sure, thank you.
Okay.
So I don't really see the novelty with the ResNets, because isn't that what the UNet is doing?
The UNet?
Yeah, like it has connections too.
Yes. Yeah, UNet. Yeah.
And that came before, right? So
yeah,
what's different?
The UNet, the UNet is in a different way, is they have this encoder and decoder structure, right? For the ResNet, the task is different, right? You have the input, you gradually, using the pooling to shrink the feature map size spatially, right? You have maybe 200 by 200 in the original input resolution. You're using pooling, to reduce by half. Then later layer, you're using another pooling to reduce by a quarter, 1/8, etc. Right? Then you apply connect, attach a couple of fully connect layer and do the classification. The UNet is, they have an encoder structure, which is reduce the spatial resolution. And because we are doing segmentation, right? The output should have the same size as your input, right? That's the classification segmentation map. We are doing pixel level labeling. So the decoder is trying to gradually grow the feature map size. Right? The UNet, they are injecting some of the feature map from encoder to the decoder, so that the decoder able to using some of the information from different stages of the encoder, right? You can different stages of the from different layers of the encoder. So I will talk about UNet when we do the maybe next week when we talk about medical image segmentation. So we'll look into that in more detail. Of course, we can discuss, right? If you have any questions or have a concern, right, in terms of novelty, we can bring this up in class and share your opinions. Okay.
Okay, thank you.
All right. Okay. All right. Thank you, guys. We can end here, and I'll talk to you on Thursday. All right. All right. Bye, everyone.
If I mean,
Yep.
is that we can talk after the class?
Yes. Let me stop recording.